Okay, so for this analysis, we are going to do a thermal stress. But this time, what we're going to take a look at is what to do when you have a thermal gradient in the model. In the last video that we did, we were taking a look at a thermal stress analysis, but we were saying that our entire part or our assembly was all at the same constant temperature. And in that case, you can do it all within a single linear stress static analysis. And in the case where you have a gradient, like we're going to set up here, in that case, you have to do a thermal analysis first in order to figure out what that gradient is, and then you can bring those temperatures into the stress analysis. The other thing that you'll see, I'm using basically the same model, but I have added a split line right down the center of the geometry, so that way we can constrain it a little bit better when we get to the stress analysis portion of our setup. So let's go ahead and we're going to go into environments, and we're going to choose to go into the Autodesk Inventor Nastran, and we're going to start with the thermal analysis. So let me just go ahead and double click, and we'll change our analysis type. You'll see that there are three different heat transfer analyses here. There's a linear steady state, a nonlinear steady state, and a nonlinear transient. So for this example, I'm just going to choose a linear steady state, and we'll say OK. And then we're going to go ahead and define our material. So I'll edit the material, and we're going to choose something out of the library here, just like we did the last time. I'm going to go ahead and select the steel ASTM A36, and we'll say OK to that. So just to make sure, we have our density, modulus, Poissons, and thermal coefficient of expansion. We'll go ahead and say OK to that. Now the next thing I need to do is set up some thermal loads, and what I envisioned is we have some sort of source on the bottom of this model that is providing 10 watts of heat generation, and then the rest of this model is just going to be convecting off into the ambient conditions. So let's rotate the model around, and on the base of the model we're going to select loads, and I'm going to define that there is a heat flux there. Now again, what I was envisioning was something like 10 watts. As you can see, for my given model, the units of BTUs per second inch squared. So converting the 10 watts to BTUs per second, that gives us a value of 0.00948. And then since this is per unit area, the dimensions on the bottom here are 4 inch by 6 inch for 24 square inches. So once we divide again by that, then we get a input value of 0.0004, and I can define the name of the load. We'll call that heat flux, and select the surfaces. There we go. All right. Now, all the other surfaces I want to select to apply the convection to. So I'm just going to start my selection going from right to left. That should grab all the surfaces except for those bottom surfaces, and we can apply convection then. So let's go to loads, and we'll set the type of load to convection. I'm also going to change the name of the load here just for tracking purposes. And for this type of load, we need to define the ambient temperature. I'm going to set that at 70 degrees Fahrenheit, and we define our convection coefficient. So just looking at some tables, for a air at 20 degrees Celsius and buoyancy type of load, that value should be about 1.09 e to the minus 6 in these units. We'll say OK to that. And there we go. So on the bottom of this model, I have my heat source, and then on other surfaces of the geometry, I have a place for heat to leave the model. So when you're doing a thermal analysis, always make sure that you have a source to bring heat into the model, and you have some place for heat to exit the model. Let's go ahead and generate the mesh, and that should be enough to set up a basic thermal analysis. At that point, we can go ahead and run it. So again, the only reason that we are doing this particular approach is because we're saying that we want to have a thermal gradient, or we have a thermal gradient in our geometry, which you can see right here. You can see that at max I have a 163, and at a minimum I'm just about 152. So when we have a thermal gradient, we have to do this in 2 steps. We do the thermal analysis first, and then we can do the stress analysis. So now that we have done the thermal analysis, of course, you want to take a look at the geometry, take a look at your results, make sure that all looks good. But presuming it does, then we can go in and set up our second analysis. So just returning from the results, what we're going to do is right-click on Analysis 1, and I'm going to say Duplicate. So now that I'm into my second analysis, let's go ahead and call that Analysis 2. I can change the analysis type. Bring that over to this monitor. And we're going to set that to be a linear static analysis. Okay. This warning just tells me that the thermal loads that I have on there are not applicable to the heat transfer or to the linear static. We'll say OK. All right, so first of all, I need to set up my constraints. So I'm going to set them up pretty similar to what I did in our other example. Let's go ahead and say free, and then on the bottom surfaces here, that's where we will apply what? How about TY constraints? And then on the back face here, these 2 surfaces, this will be our TX constraints. Okay, and then the reason that I split this model so I can select the center line or edges there and apply TZ constraints to those. So let's go constraint, and I'm just going to draw a small rectangle around those edges. You can see it grabs all those edges, and there I'm going to apply TZ. So that way when we do the thermal expansion in this model, it can expand away from the center line of the geometry. There we go. All right, so there you can see I didn't give the constraints in this particular case any names. It's a little bit hard to tell maybe what you have there. So that's why I get in the habit of, or try to get into the habit of naming my different constraints and loads. Maybe we'll edit them real quick just so I know what they are. So there's my TY constraint. So that way when I open this model up some other time in the future, I don't have to be interrogating the model to try and figure out what's what. In my setup, I can just look at the model tree there and I know what everything is. That way, if I need to make a change, I can quickly do that, or if I want to understand what it was that I set up prior, it's pretty easy to do. All right, now we have all of our constraints set up. The only thing we're going to do for the loads are those temperatures relative to a stress-free reference temperature. So the stress-free reference temperature is going to be similar to what we did, or the same as what we did when we did this all within the linear static stress analysis with a constant temperature, and that is we go to loads, and in the loads we're going to go to the initial condition, and I'm going to call this initial temp, and we'll say that our stress-free reference temperature or our initial condition is 70 degrees Fahrenheit. All right, now is the part where it gets a little bit different, and that is we need to apply what it is, our delta T, the temperatures that are going to cause the expansion or the contraction. And in this case, those temperatures were in the steady state heat transfer analysis. So when I go to loads, in loads, what I can do is say that I want to grab the loads from output. All right. And basically that's saying that the input for this analysis is the output from some other analysis, and that output can be the temperatures from the steady state heat transfer that we did. So all I have to do here is click this little ellipses button, and I can browse for those temperatures. So let me browse down into the folder. This model is called Thermal Expansion - Thermal Gradient. So I'm going to scroll down here. So there's Thermal Expansion - Thermal Gradient. Because I've been working inside of Inventor with this file, it creates that folder for me once I get into Nastran. And in Nastran, you can see that it creates an InCAD folder, or in that directory, we can see that it creates an InCAD folder. Inside there is an FEA subfolder, and then there is the Nastran output file. That would be the temperatures that I want to read in for this analysis. So we can say OK to that, and at that point, we are ready to run the analysis. There we go. And there we can see our results. By default, we're looking at the stresses. Nice low stresses in the model. Remember, the temperatures were somewhere around the 130 to 150 range, and we told it was stress-free at 70. So we don't have a very large delta T. If I take a look at the back of this model, that's probably the easiest way to see the expansion. So you can see the dashed red line, which indicates the initial position of this geometry. So you can see that we have expansion in the y direction, right? So it's growing upward from the constraints in the y direction that I have at the base of the model. And then you can see the dashed line here and the dashed line here. So I'm getting expansion both in the minus z direction and in the positive z direction. So it's growing outward in those directions. And then if I move to a side view, as far as the y direction is in an x direction, really, you can see that we're getting growth in the minus x direction and also growth in the y direction based on this edge right here, or these two edges right there. Okay, so that's a little bit about how to perform the thermal analysis first, and then to map those temperatures into your linear static analysis. So hopefully that makes sense and gives you some good information. Thanks for watching. Have a great day.